We will record the talk itself. I'll shut off the recording for the Q&A just to save time. All right, go ahead, Livia.
Okay. Can you see the slide?
Yes, looks fine.
Okay, perfect. Thank you so much for the introduction, George. So today I'm going to talk about core edge integration in Tokamaks. I would like to thank the organizer for inviting me to give this presentation on this topic that is very important right now in our fusion community. As George said, I have been working for some time at D3D. Before that, I was at the Max Planck, and I had the great opportunity to work also on ASICS upgrade. So did really important work on both tokamaks. So I actually I add some slides on the work that I did at ASICS as well. And so I will start introducing here what the core edge is. So really integrating the hot core with the cold edge is the greatest challenge in tokamak research. If we like, we can divide this challenge in two. On one side, we want to achieve high gain in beta steady state scenario compatible with power handling solutions. And the way that we try to address this is to use a shape flexibility and a heat and current drive to explore scenarios. The other challenge is to control divertor heat flux without degrading core performance. And for this, we try to use innovative divertor solution to achieve detachment compatible with the core, using as actuator divertor geometry, plasma drift, control of impurities and transient. So what we do in core edge as right now, we really try to dive deep in the physics understanding and try to establish a basis for integrating the hot core with the divertor scenario optimization and develop tools for predicting capabilities. So as an outline, I will introduce even more in detail what we mean for core edge. I will talk about radiative cooling and impurity transport studies. We will see some example of the divertor detachment and the radiative and detached divertors, in particular in closed geometry. And then I will summarize and we'll dedicate some time to discuss consideration for fusion reactors. Now, as the word say, core edge is quite of a wide field, so it really spans from the core to the edge. And so what I have done here, I have made a selection of really relevant topic for core edge on which I worked extensively. That being said, that there are other points which are important as well, and they will need to be added to the list. And this is something that I would happy to talk about also in on another time. As a start, let's start from the fact that plasma confinement is a key factor for the design of a fusion reactors. However, is limited by the heat transport. So what happens is that we heat in the center, but then the heat and particle flux diffuse towards the edge, and then following the magnetic field line, reach the divertor region, which is the main region of the plasma exhaust. Now, if we do not mitigate these power fluxes in future reactors, these are going to be above 300 megawatt per square meter. And the material limit, however, tell us that these fluxes needs to be below 5 and 10 megawatt per square meter. And at the same time, we need to keep the temperature below 5 eV in order to reduce erosion. And so this means that we need to increase power dissipation to more than 95%. And this just gives us an idea of the magnitude of the problem that we have in front of us. And so the question is, how can we reduce power load to match the technological limit? One way is through radiative cooling to promote radiation while minimizing core contamination. And in doing this, we need to make sure that radiation is compatible with dilution, WMHD, divertor, impurity leakage, and core accumulation. The other way is through divertor detachment, is the achievement of a cold dissipative divertor will reduce heat and particle flux. Now, detachment often, especially when we obtain it with high gas path, lead to a decreased confinement, however, not always. And this is where we start to see where the problem is, where we have fundamentally the core and the edge that are governed by different physics. So on one side, we have the core and the pedestal, which needs low collisionality for a current drive, the achievement of a pedestal pressure, so for performance. And on the other side, we have the diverter, where we need a high density and impurities for dissipation. The two completely different words meet at the separatrix, which really constrains both core and diverter performance. And so the compatibility of the core edge solution balances here at the pedestal, where any pad is set by a core fueling and a radial transport to the separatrix density. Any pad, any SEP is set by a divertor detachment and parallel transport. The simultaneous requirements for a core edge integration are, well, first of all, we need a robust pedestal, so high pedestal pressure also requires a high power crossing the scrape-off layer. But high power crossing the scrape-off layer also means that we need sufficient mantle radiation to control these PSOL. And so we have to understand the effect of impurities on the core, on the pedestal, and on the diverter. Additionally, we need to make sure that we have acceptable any SEP, any pad ratio for robust detachment and pedestal. This determines the pedestal stability, but is also set by the diverter pressure. In this way, coupling with the diverter closure is synergistic because, as I'm going to show in the next slide, detachment in a closed diverter is more compatible with the core needs. So this is the main question we are going to try to address through the talk. Radiative cooling by impurity seeding. I wanted to start saying, how can we choose the right impurity seeding if I want to radiate in a specific region of the plasma? The answer comes from the atomic data. I'm plotting here the LZ as a function of the electron temperature. And as we can see, while carbon and nitrogen are the most suitable edge radiator, we can see that argon and krypton still radiate significantly at high temperatures, and therefore they are best candidate for a mantle radiation. In comparison, if we are going here and now we enlarge this plot towards a higher Z, we can see that tungsten has its force maximum at around 1 kV. And so it radiates into the core, where the losses must be avoided to not reduce the fusion gain. And this is a problem. This is a problem in tungsten machines, such as upgrade, in-ITER, and in future reactors, because we really need to restrict the concentration of tungsten into the plasma. Now, this technique of impurity seeding is already required in a tungsten machine, because now they are missing the intrinsic scrape-off layer radiator, which, for instance, in this 3D is carbon. And it will be necessary in future reactors, which will need maximum diverter radiation and a strong mantle radiation. I wanted to show here this example from Aztec's upgrade, where the injection of nitrogen lead to a confinement improvement. So we performed this discharge, and when we inject nitrogen here into the plasma, 2.5 seconds, we saw that the radiation was increasing. However, the plasma store energy was also increasing. And therefore, we wanted to study the effect of radiation on energy transport. And by doing this, we went to look at power balance with and without, including the radiation, and we could indeed confirm that the radiation was located at the edge. An analysis of the chi with the transp analysis showed that chi was varying only a little if we would include or not include the radiation into account, really confirming that the core transport wasn't changing. Later on was demonstrated that the confinement improvement is a fact, a pedestal effect, which then propagates to the core via profile stiffness. We also did experiments where, in addition with nitrogen, we use a krypton for mantle radiation because, as I mentioned, future reactors are going to need both divertor and mantle radiation. And so what happened here is that when we inject krypton, which is here in green, we could see that we could still increase the plasma store energy. However, when we attempt to increase the krypton gas path, we started to see, and this is very clear shown by this tomography reconstruction, that we were entering a radiation collapse. So later on, we with some calculations, we were able to calculate that a krypton concentration below this amount that I'm writing here was needed in order to avoid impurity accumulation in the plasma. Now, while we treat impurities, important effects that we need to take into account are these non-coronal effects. Practically, impurities enter the plasma as neutrals, and then they are subsequently ionized. Now, if we neglect the plasma transport, we have a balance between ionization and the recombination, as in the solar corona, which is why it's called coronal equilibrium. And this situation is fulfilled into the plasma core. In this case, the radiation can be calculated as NZ, NE, and LZ as a function of the temperature. However, at the plasma edge, where we have a steep gradients, as we can see here, and we have the ELM, so this edge localized instability, which flush out impurities and so on, we cannot neglect the radial transport. And therefore, we have a situation that we call non-coronal equilibrium, where LZ is not only a function of TE, but is also a function of NT tau, where tau is the resident time for an impurity. So we try to look into this effect by coupling the Astra transport code with the Strahl impurity transport code in order to study this self-interplay between the background plasma transport and impurity transport and the ELMs. And what we found out was that non-coronal effects are important for nitrogen, so for low Z impurities, but not for high Z. I'm showing time traces for nitrogen on the left and for tungsten on the right, a different radial position inside the pedestal, at the very edge of the pedestal, and in dash for coronal equilibrium, and in a solid for calculated by Strahl. And so what we can see is that there is a difference of a factor between 2 and 5 between the radiation, which is given by Strahl, and the one that is given by corona, showing the importance of these effects. Whereas in the case of tungsten, coronal approximation is a good approximation, and the reason is because tungsten has a very high ionization and recombination rates. And these are important details that we need to keep in mind whenever we go and extrapolate for reactors. Now, these time traces I'm showing here are done at an L frequency of 140 Hertz. Now, what we have done is that in the simulation, we change the Helm frequency, keeping the Helm energy loss constant. And we put the frequency of the Helm at 10 Hertz. What we found out was that the radiation of nitrogen wasn't really changing, whereas the radiation in the tungsten case was increasing of a factor of 4. And as we can see, these different behavior between nitrogen and tungsten can be explained in terms of profile peaking. This is driven by the neoclassical transport, which is proportional to the charge. And so practically at low Helm frequency, tungsten has a time to develop a very peak profile. And so the radiation, as we can see here, keep on increasing till the simulation crashes because there is more radiation than at the power source. And this actually was in agreement with what was reported in the experiments in this paper from Schweitzer 2011, where an Helm frequency of at least 12 Hertz was required in order to sustain the discharge. And so this study has shown the importance of having Helm frequency in order to control tungsten in the confined region. And we are coming back to this topic of impurity buildup in the pedestal in few slides. Now, the other way to reduce the power loads at the target is through divertor detachment. Now, it has been shown in a number of tokamaks that the detachment onset is influenced by divertor configuration through variation in divertor target and baffle geometry. I'm showing here on the left an example from Arcatur CMOD, which have experimented different kind of closure and target shaping. And so what the 3D did recently in the last few years, it went and implemented a different degree of divertor closure, such that as today, we have an open lower divertor here in red, a closed upper divertor, and a small angle divertor, which is the SAS divertor, and this is characterized by high closure and target shaping. Experiments at D3D have shown that the upper close and the slot divertor can detach a lower upstream density than the open divertor, which is also more compatible with the core. And this has been confirmed by the simulations as well. Now, of course, the question here to be asked is, which are the processes that lead to this detachment and lower upstream density in the closed diverter? But in order to pin down the physics, we really need to use a coupled fluid and kinetic codes. Now, I really like to show always these figures here on the left, just to give an idea of how complex is the edge physics. Like down there, the physics is crazy. We have impurity radiation, ionization, dissociation, recombination. And so this is exactly the reason why we need to use codes like a SOLPS, scrape off layer plasma solver, which is the coupling of B25, a multi-fluid plasma code with Irene Monte Carlo. So practically the multi-fluid code provides the background on which the neutral trajectories are calculated, and then Irene computes the sources and the sinks due to neutrals and gives this information back to B2. Now, one thing that we know well, so is that as soon as the power crosses separatrix and follow the magnetic field line, is going to meet the impurity radiation zone. We are here around 10 eV. Here carbon and nitrogen radiates very strongly. These allow the temperature to drop around 5 eV, where the ion and the neutral interaction zone is found. Elastic collision, charge exchange now allows the temperatures to drop even further and reach the recombination zone, which is around 1 eV. And now the divertor is finally detached. But what is exactly divertor closure? The term closure refers to the degree in which the recycling neutrals from the target can escape the divertor. And I think that this plot is a good way to show what really is. These are plots from Monte Carlo trajectories from Irene. And on the right, you can see that these trajectories are scattering everywhere. Instead, in the closed divertor, we can see that neutrals can really accumulate at the target. When we started to look into this work, one of the first things that we did was to provide a metric for divertor leakage. We define a DLP parameter, which is the ratio, which we define this as a duration of the neutrals that can escape the diverter over the neutrals that are born in the diverter. And as I'm showing in these figures here on the left, the percentage of neutral escaping the diverter at the detachment onset is 12% for the closed and 35% for the open diverter. I'm showing here on the right the ionization to deionization contour plot. We can clearly see that the baffle in the closed diverter is preventing neutral, so there is not leakage up here going all the way to the midplane, whereas in the open diverter, neutral are free to escape all the way upstream. And so the baffle keeps the neutral right down at the target. Now, the increased power dissipation in the closed diverter is due to a combination of impurity radiation and volumetric losses. I'm showing the open diverter on the left and the closed diverter on the right. And we can notice that in the closed diverter, we have a higher P net, which is almost 40% higher than in the open diverter. And this is due not only to an increase in the line of radiation. Carbon remains the dominant radiator. However, we can see that in the closed diverter now we have actually an increase in the neutral radiation and in the ion neutral losses that we just discussed. And in fact, the relative contribution to the carbon itself is reduced. Now we were able to find out and demonstrate what is the actual mechanism for detachment at lower upstream density. This is not just an increase in the radiation, but it's also a reduction in the convective term. I'm showing the open diverter on the top and a closed diverter on the bottom. And in green here, we have the parallel convective fluxes, and in magenta, the conductive fluxes, whereas in red here, this is just the electron temperature. In simple word, what is happening is that in the closed diverter, the neutrals cannot escape, and therefore there is no particle flow. In fact, we can see here, we don't see the convective part. But then if there is no convection, the heat needs to be carried out by conduction, which has a very strong density dependence, as we can see from the equation. So now if we consider the upstream density from the 2-point model, and we are going to solve the equation for both geometries. At the detachment onset, we will find a ratio between the open and closed diverter for the upstream density, which is very consistent with what we found at detachment. This investigation was able to not only to show that indeed we detach a lower upstream density in a closed diverter, as was shown by experiments, but we were able to really get a hold on the mechanisms that are behind these detachment mechanism. Now, what we did going forward was to try to combine radiative cooling by impurity seeding and detachment with divertor closure. So here we started and we did a very comprehensive work on the effect of divertor configuration and radiative species in D3D. At first, we look at the effect of divertor geometry in seeded H modes. So practically, we choose an impurity, in this case, nitrogen, and then we vary the divertor geometry. So in this case, we changing the strike point location in the slot diverter. And then we fix the strike point in the slot in the position that we find out from this previous analysis being the best position for impurity retention, and we change the impurities. In particularly, we went to compare nitrogen with neon, because nitrogen is a good divertor radiator, but is problematic in future reactors because of ammonia formation. And in fact, neon would be preferred because it's chemical inert. And so this is one of the reasons why ITER really wants to know if neon is going to work. So I'm showing here an example of nitrogen in the SAS inducing pronounced detachment without affecting the core. So at 3 seconds, we inject nitrogen, and this in the diverter. And as we can see, there is a very important increase in the neutral pressure, which correlates with a very low temperature. But the WMHD is not changing, so the core is not affected. We are able to achieve a very low temperature in the diverter. After 4 seconds, after this second step, the diverter Thomson is actually measuring temperature of roughly 0.5 eV. And this is independently confirmed by the infrared spectrometer, which actually detects the appearance of the passion line series, which only appears when the temperature is below 2 eV. So this experiment really was the first simultaneous observation of detachment on the entire boundary diagnostic, was viewing the SAS, and I put a list here. But this was really indicating that the simultaneous data was suggesting that the detachment was not a highly local phenomena, but we were actually able to see this through the entire slot. Now, a very interesting thing that we found whenever we were doing these experiments is that we saw higher level of relative nitrogen contamination in the core. And in addition, also the fact that we needed a higher nitrogen to detach whenever the strike point was located in the outer corner of the slot. So here in red. So here I'm showing JSAT rollover from the non-mirror probes. As we can see, in the case at the outer corner, we need the second nitrogen path for JSAT to roll over. And also we saw, and these are profiles for the impurities into the core, we can see that there is a nitrogen profile which is higher, and this is consistently through all the data set that we have built with different power and different density. So in order to gain some insights on this very interesting physics, we went and start also here some modeling. In this case, I use SOL-PS either with full drifts and multi-impurity species and neutral collision. This work has been done for the first time at D3D with the inclusion of all these models, E cross B drift, gravity drift, viscosity, currents, and electropotential. And we were really able to pin down the importance, for instance, of drifts in a divertor, which is closed as the SAS. Now, particle drifts are induced by electric field in the divertor, and these arise from gradients in the T profile. Now, in these experiments, the ion B, grab B, was inside into the diverter, and in this direction, drift tends to move particle from the outer target to the inner target. And so here I'm showing the 2D ionization profile with drift on the left and without drift on the right, so that we can see what the effects of the drift is in moving this particle. However, the ionization distribution is not only affected by drift, but is also affected by divertor configuration. In this case, the 2D ionization profile is with drift included, but on the left for the strike point at the inner surface, and then on the right for the strike point at the outer corner. Now, different strike point locations correspond to different wetted area with a different distribution of the ionization source. And this is why we can see that in one case, the source is tightly trapped in the slot, whereas in the other case, the source is outside in the common region. Now, the reason why this is important is because divertor geometry influences the plasma flows via modification of the ionization source, and this has important consequences on impurity transport. A flow reversal, a flow away from the diverter, so in this case, these orange and blue and green zones that you see here, occurs in a flux tube where the ionization source exceeds the ion loss. This has been theoretically predicted and also experimentally verified. Now, why this is so important here is because the main ion flows and consequently also flow reversal actually enters the equation for the impurity transport. The impurity transport is basically dominated by this term, which is impurity colloidal velocity. Now, we don't have to enter in the detail of all the equations, but just to keep in mind, the colloidal velocity depends on the main ion flow, which I'm showing here, and also on the drifts. So if now I go and I plot these terms, what we found, so I'm showing the main ions on top and the nitrogen flow on the bottom, on the left for the strike point with at the inner slanted, and on the right with the strike point at the corner. We can see that we find a flow reversal for both main ions and impurities. But now with flow reversal, all the forces are directed away from the target, and therefore this can lead to impurity leakage. If we compare the nitrogen flow, we can see that in the case where the strike point is at the inner slanting, there is nitrogen is indeed better retained, And so it can at least qualitatively explain the experimental results of why we found less nitrogen in the core in this divertor geometry, and also why we needed less nitrogen to detach. So now I'm going to describe the other part of the experiments that we did. So now we fixed the strike point location and the inner slanted, which we thought and we found was the best. We just demonstrated was the best location for impurity retention, and then we vary the species. So as I'm showing here, neon turned out to increase the radiation in the core. This was expected just by looking at the LZ function. And also we can see from here that the alpha signals, which gives us some insights on the ELMs, and I'm plotting the ELM frequency here, is dramatically reduced with neon. So now what is happening with neon is that neon radiates in this mantle, and by doing so, it reduces the power flux through the separatory, and this reduction of the ELM frequency can favor the impurity buildup, as I'm going to show in the next couple of slides. One important consequence of the neon dissipation upstream is the fact that we can have detachment or at lower upstream density, which can be important for core edge integration. And this can be shown by, again, considering the expression for the upstream density from the 2-point model. And so, as we can see, neon reduce both Q parallel and 1 minus F rad because of this dissipation upstream. And the implication, just by looking at the equation, is that for a given temperature at the target, we need the less scrape of layer density, which can be favorable for a core edge integration. And this is exactly what we found plotting the profiles that with neon we have here this lower scrape of layer density. Now, another important findings was that neon penetrates more effectively into the pedestal. So if we really look and compare the profile between nitrogen and neon, we can see that while there is not much nitrogen going into the core and the pedestal is not changing much, for neon, we can see that neon enters the core and the pedestal gradients are steepening. Now, this different leakage behavior is fundamentally linked to the detail of the scrape of layer impurity transport, which I'm not going to describe here, but actually I'm presenting this at the APS next week. So if someone is interested, can follow the talk there. But just something to be kept in mind. And so this is, again, we are talking about core edge integration, how much whatever happens in the divertor is going to impact the pedestal. And here, this slide seems complicated, but I'm going to guide you through. This is really now putting all the pieces of the puzzle together. So we start from the divertor. We know that the neon is pushed out of the divertor, is leaking out, now is in the pedestal. What happens is that the neon is building up. We see this very clearly from this plot here. And now in the pedestal, also see an increase in the diamagnetic frequency. The diamagnetic frequency is responsible for an improved pedestal stability, which together with the radiative mantle is the cause of this reduction in also the ELM frequency. But now with the less ELM frequency, if you remember what I showed at the very beginning was what was happening with tungsten. we are actually lacking the capability of flushing out these impurities from the pedestal. And so the neon starts to build up in the pedestal. And so we started a self-enhancing mechanism of the neon build-up, and this eventually can lead to accumulation. Now, this is exactly the reason why operation with neon in tungsten machines of a medium size is very difficult. And this is also the cause for tungsten accumulation in tungsten machine. Here, because we have a carbon machine, we are actually able to see all this evolution of the profiles, and actually in this case we don't encounter collapse by radiation, but this is exactly what happens instead if we are in a tungsten machine. We put together a core edge integrated scenario with an edge solution compatible with good core performance. And so what we can do, for instance, we shown here that we can choose an appropriate species for pedestal conditions. We can choose and optimize a divertor geometry, or we can also tailor the drift for a particle entrainment. To summarize here, the path to an optimized core edge integration relies on radiative power exhaust balancing core contamination. Impurity seeding, which is necessary for power exhaust, can also lead to confinement improvement as long as the central radiation can be controlled. We have seen also the importance of coronal and non-coronal effects, which need to be taken into account. Divertor closure is beneficial to high density divertor and reduce neutral leakage, both helping the core edge integration. I show some research strategy for combining divertor geometry, plasma flow, scrape off layer, core and impurity transport. I do have a part where I now discussing consideration for future reactors. I will try to be short here. Now, what the reactor, so as right now I show core edge integration on existing machines, experiments and modeling. However, the situation in the reactor is going to be different. Reactor will need to satisfy high pressure, low density, opaqueness to neutrals, and control high divertor density, a robust detachment without transient loss. Additionally, the Mantle radiation that we discuss in detail in this talk is in fact limited by several factors. One is the fuel dilution that we discuss, so we cannot allow the lot of concentration in the core. But then there are other causes, MHD stability, which I didn't discuss here, or the impact of this effective on the stability and turbulent growth rate. But also the Mantle radiation is limited by the need to stay in H mode. So because of P sol needs to be above the power of the LH, we end up with this scaling of a Q sol proportional to magnetic field, radius, and lambda Q. And I just want to point out that this scaling is driving the major diverter exhaust challenge in H mode studies. This is the reason why we will need advanced diverter solutions, where for advanced, I mean also expensive solutions. These lead the community to ask ourselves if the H mode is the only way to go. This is a slide I presented at the D3D Program Advisory Committee earlier this year in May to discuss plans for D3D. And this is where we made a case, for instance, to study negative triangularity. Negative triangularity offers a fundamentally alternate approach to core edge integration by avoiding to go to H mode. by avoiding to go to H mode is pretty much removing all these this issue that I just listed. However, we do not know if a negative triangularity scenario can extrapolate to favorable steady state reactors. The physics basis is still limited, but it will merit further investigation, and this is something that we are going to investigate in the next campaign, D3D as well. This is my last slide. I would like to conclude saying that the challenge for Courage integration is really to establish the physics for simultaneously balancing core and divertor solution, balancing shape, fueling, and radiation, understanding impurity transport in reactor condition. It will be very challenging. The question is whether the impurity transport in the core will be reduced due to a lower density gradient and an increased temperature gradient, which is foreseen for ITER. This could lead to a transition from the inward pinch to an outward screening, so avoiding the accumulation that we talk about. Another important issue is to understand the effect of neutrals on the separatrix and on the pedestal structure. And so neutral impurity trapping, another topic that I touched base during the talk. And finally, this Courage integration is really pushing towards the integrative modeling through multiphysics and multi-scale solution. I would just like to say that this is a really great field to work on. And so if you are interested in work in this field, just let me know. I'm actually looking, just started search for a postdoc, and there are several opportunities to get involved in working on Courage. Thank you very much.
Thank you, Livia. Very nice talk. We have, I'll stop the recording, and then we have time